Electrons are arranged in shells around the nucleus. Within shells, electrons are actually arranged in special areas of particular energy levels, called orbitals. Orbitals come in different shapes and are named using different letters, S, P, D, and F. Each of these orbitals can hold varying numbers of electrons. S can hold 2, P 6, D 10, and F 14.
Transition metals are unique in the periodic table in that they are the only elements that contain partially filled d orbitals, and these are key to the colored compounds and complexes they form.
The number of electrons in each orbital depends on the atomic number, which we know indicates the number of electrons in an element. Groups 1 and 2 make up the s block. Elements found in the first column contain 1 electron in the s orbital, while elements in the second column contain the maximum amount, 2, in the s orbital. As we move across the periodic table, elements in groups 13 through 18 make up the p block and can contain from 1 to 6 electrons in their p orbital depending on which column they are in. Elements in groups 3 through 12 make up the d block and can contain from 1 to 10 electrons in their d orbital.
However, as atomic number increases, we must account for the preceding orbitals. For example, nickel has an atomic number of 28, meaning it has 28 electrons. It is in the d block and in group 10, so it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its d orbital. But remember what we said. Because it is in the d block, we know that its preceding s and p orbitals are both full.
Copper, silver, and gold are all in the 11th row of the periodic table. This means they should have 9 electrons in their d orbital. However, elements in the 11th row generally have 10 electrons in their d orbital.
Since a full d orbital is preferred over a full s orbital, the d orbitals in copper, silver, and gold actually steal an electron from the outer s orbital to become more stable, leaving them with an s1 d10 configuration.
Although sunlight appears colorless, it actually embodies the full color spectrum. When sunlight hits an object, the object absorbs certain colors, and the color that it does not absorb reflects off the object, making it appear that color.
For example, an apple appears red because it absorbs all of the colors in the color spectrum except for red, so we see a red color because it is reflected.
Out of the 3 metals, copper, gold, and silver, we would think that silver is behaving differently because of its dissimilar color, right? Let's see.
Because copper and gold steal an electron from the outer s orbital to fill up their d orbital, they absorb blue and red photons through these electron transitions and thus reflect and appear yellow to the eye.
Then why is silver, which is in the same group as both copper and gold, not the same color?
The atomic radius of silver is 16.6 picometers larger than the atomic radius of copper, allowing a bigger distance between the s and d orbital, which restricts the electron transition.
The difference is too large for the electron to jump.
In copper, the s and d orbitals are close enough to allow the transition, so it appears yellow, and silver appears colorless.
But now we face another problem. The atomic radius of gold is only 0.3 picometers smaller than that of silver.
If we use the same logic, shouldn't gold be colorless too? No!
This is because of something called the relativistic effect. As we go down the group in the periodic table, atomic size and mass increases.
This causes the s orbital to contract to a greater extent.
As the s orbital contracts, the energy level shifts closer to that of the d orbital.
Now the electron can make the jump, so gold is the metal that is behaving differently than we would expect because of the relativistic effect.